Hi there. Hi, and welcome to today's lesson for TTED 4044 structures. Now, this is built around the lab that we're doing this week, where we're going to look at compressive stresses of materials. In particular, we're going to be looking at the compressive stress of little pieces of laser cut MDF, because in a little while we're going to be using laser cut MDF to build a truss. And you're going to have to know how this material fails when loaded in compression. So I've got some samples here that I've cut up in advance. And for the purpose of this demonstration, I've got a number of different lengths right here of material that is, and take out your calipers to measure it. Set it to metric, of course. And let's see right here. This one is measuring 3.87 millimeters in width by 3 millimeters in thickness. Now that makes sense because the 3 millimeter thickness is a pretty standard thickness for medium density fiberboard, or the hardboard that we're using in shop. Sometimes you'll see it sold as 1/8 inch material. It cuts really nicely on the laser. So just jot that down in your lab that you're working with what I'm going to refer to as a 3 millimeter by 4 millimeter section right here. Okay, and we'll talk about why that's important a little bit later on. But even though it's actually 3.8 millimeters in this direction right here, keep in mind that you can see from the burn marks that that's the sides that the laser got cut out on. And all of our samples will be slightly underneath their nominal size. So we'll use the nominal, or the named size, 3 millimeters by 4 millimeters for this sample. But due to the curve of the laser as it came along and cut right along here and cut right along there, we've lost about 1/10 of a millimeter from each side of that. And that's something that you're going to have to keep in mind when you're designing your bridge or your truss in AutoCAD. For laser cutting, is that the pieces that you get off the laser are going to be about 1/10 of a millimeter narrower on each side than what you designed in AutoCAD, because this was designed to be a 4 millimeter piece. Now what we're going to do with this is we're going to put it on our testing jig right here, and the testing jig is kind of described right up in this section right here. We've got a test arm that's going to connect right in here, and this arm is well, let me plug it in right there with a screw and let's see what happens. Let's test our first piece right here. Now, to measure how long it is, easy enough to do. Just line it up with the center right there. This is a 30 centimeter long piece, or 300 millimeters. So I'm starting with a piece that is 3 millimeters by 4 millimeters by 300 millimeters long. Okay. So when I put that in here, it's pretty easy to figure out where the bottom of the test jig is going to have to be. It's going to have to be sitting right here. And you can see that that's going to sit right on that hole right there. So I'm just going to slide this in between these two pieces right here. And by sliding it in between, that means that it's less likely to flop off to the side should we have to apply high loads to it. There we go. And I can put a little nut on the back right here, again, just to help keep it from flopping off to one side. Okay. And when you put that nut on, don't do it so tight that this doesn't swing freely. This has to swing freely because this is our little lever arm jig that's going to allow us to calculate the amount of force that's going right through there. Double check to make sure that when you put this in here that stands up and that this arm is nice and square, because if you make it all nice and square and perpendicular, the math gets easier. Okay, so right now this is supporting a load, and as you know from our moments calculations earlier in the course, that the further out this comes, the less load it has to support, because what we've got here is we've got a moment or a torque situation. And as you can see from the fact that that arm will swing down all on its own, it has mass and distance right here, so it's got a torque that is pushing it downwards this way. Now, to simplify our calculation for how much load that's exerting on here, I've calculated in CAD the centroid, or center of mass, for this arm. And that exists 26.8 centimeters, or 268 millimeters, out from the pivot point. So when this arm is just sitting here, it has a mass of 41 grams. So in other words, 0.41 newtons of force. And that is causing it to swing downwards. And we can pretend that the lever arm of the entire arm is focused in the equivalent of 41 gram mass acting 268 millimeters from the pivot point. That's what we mean by center of mass, or centroid. We can just assume that the entire structure acts through its center of mass, saves a whole bunch of calculation right there. In fact, enables us to do calculations. So even without a weight being applied, our test member right here is already supporting a force, and you can see I've jotted that in up there, and I don't know what the resolution's showing up right there, but that says we've got 0.41 newtons at 268 millimeters. So that shows up in our compressive load formula, cleverly hidden right behind that arm right in there. And the compressive load formula says brackets 0.41 newtons times 268 millimeters. So the force of this arm times the distance at which it acts, plus the force of a mass that we're going to add to the structure, and I think I might start with something a little bit heavier, times the distance that works, all divided by the distance that our member is out from the pivot arm. And those numbers all cancel out nicely and give us a stress, well, actually a force. We need to divide by cross-sectional area to get the stress that's going to be acting right in there. Okay, now you can kind of give it a little push to see how sturdy that is. It hasn't started to buckle just yet. And so I'm just going to come in here, and because 500 millimeters is a nice place to start measurement, I'm going to put my 500 millimeter load right out there. And you'll see that this member right here, our compressive test sample, is sitting at 34 millimeters, and it hasn't buckled yet. It's still supporting that load. Hasn't quite started to bend out to the side. So I've got a couple ways that I could increase the load. I could increase the weight out here, because that would increase the amount of force acting down. I could move this load out towards the end, because that would increase the distance that it's pulling down at. Or, and this is probably the quickest way to do this, I just use one hand to lift up here gently, and I start moving this member inwards. Now make sure that you keep it lined up perfectly vertically, okay? So nice and square in here. And you can use these little laser lines down here at the bottom to match it up, because just as each of these holes along the top is spaced by 1 centimeter, so is each one of these finger joints down at the bottom. So as we bring it in, now the D2, the distance from here to here, is getting smaller. So the force in here has to go up, because the torque coming down this way, the moment coming down this way, is constant. I haven't changed that. So as my lever arm goes down, the force must go up. And now let me just rotate that so you can see it from the side right there. As I start to put the force on there, you can see that when I apply that, there's starting to be a little bit of a bend right in here. Now, as soon as you see that bend, it's a good idea to just write down in your notes that bending starts at 250 millimeters, 25 centimeters. Okay, and you know, when you see that amount of buckling in there, you can say, well, that's probably buckled, and if I bring it in a little bit more, it's probably going to fail. Let's come down to 23. We'll see if it can handle 23. And oh, it handled 23. And you want to be really gentle as you start getting in here, because you're getting very close to where this is going to snap. Handled 22, so it is still supporting that force. Now, when you do your tests on your truss, it's going to have to support that load for 30 seconds. So feel free to leave this here for a little while. This is bent enough that I'm starting to think that we could call it buckled, but I'll come in 2 more centimeters just because videos are always more fun when you see something actually. There we go. Okay, so that one, it's totally buckled on, and let's come up to 21 right here. 21 it's buckling at. And now that it's bent one, so we'll say that it's still good at 23 centimeters. Okay, so it holds at 230 millimeters. So what I can do now is I can say, okay, this was a 200 gram weight, so that's 2 newtons, okay? And the 2 Newton weight was acting at a distance of 500 millimeters. So I can sit down and do a little bit of math. And let's see if this will stay up while I write on it. So my force is coming down this way. Okay, I had the 0.41 newtons. Times 268 millimeters. And then I also had my 200 gram load, okay, which was 2 newtons, acting at 500 millimeters. So those two were acting together to come down that way, and they had to be equal to the force in the compressive arm, the compressive force. Just making sure on the screen that you can still see that. It's a little bit small, but that's why I'm reading it out as I say it, times d2, which was the distance right out here, which when it broke, d2 was 230 millimeters. So now if I want to find out what the force is, I just divide both sides by 230. And I should get the force in that arm, and I'm using my calculator as the camera right now. So 0.41 newtons times 268 millimeters plus 2 newtons times 500 millimeters. I'm just going to pause this. And do I have a pause button on here? Don't tell me I've only got a stop button. How do I pause this thing? Come on, just let me. Okay, so I'm going to have to edit that back together. But so went through and did all the math right here, divided it all out, and I came out with a number that tells me that when this failed, in fact, here's the other part of it right here. When that failed, it failed at 4.83 newtons of force pushing down on it. Okay, now when you've recorded that data, come on in, you've got a data table right here. And you can see on your data table that you've got, that was a nominal 4 millimeter wide beam. They're all 3 millimeters thick. And that one we said was 300 millimeters long. So I can come right in here and say the 4 millimeter at 300 millimeter long was 4.83 newtons. Okay, so write that down in your table, and then you've got a log chart right in here, and I want you to put these on the log chart because this is going to help you figure out the compressive stress of intermediate length beams, because you're not going to measure every compressive structure that you might use, but you're going to need to know how strong they are. So I'm going to show you some formulas that can help you with that, but for right now, just plot it onto the chart right here, and at 300 millimeters long, that was, I did say that was 300 millimeters, yes, at 300 millimeters long, that failed at 4.83 newtons. Now, if you're not familiar with log charts, keep in mind that the way the log chart works is you start here at 1, and then 2, 3, 4, 5, 6, 7, 8, 9, and when you get to 10, Now you're counting in tens, so this is 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, and now you're counting in hundreds, 100, 200, all the way up to 1,000. And what this lets you do is this lets you have really big numbers on your chart and represent them with the same resolution that you do really little numbers, because if you didn't have that, if you just had a linear scale along here, all of your little numbers would be crammed into a space from here down to here, and you'd get no resolution between them. So just find a spot on there for the 300 millimeter long section at 4.83. That's just below 5. So 1, 2, 3, 4, 5. And we'll put a dot on there, and we'll say that our dots equals, that is our 4 millimeter Okay, so there we have a little dot, and just jot a legend down on the bottom that the dot indicates 4 millimeter nominal, so we know what we're talking about later on. Okay, let's try this with a couple of shorter members. So we'll come back in here. Yes. And now we need to adjust our jig. Now if you're testing different widths, then you can find another 300 millimeter length. You could find a wider one, and you could test it right now while you're still set up for 300 millimeter lengths. But my next length in here looks like it's going to be 250 millimeters. So I can drop this down. Now keep in mind that we've done a nifty little trick in setting up our arm right here. These holes are only spaced 2 centimeters apart. So in order to make this arm work right here and get nice and level right there, you just need to flip it over. And now this can slide in right here, and we're testing a 250 millimeter specimen. Now, according to beam buckling formulas and all that, we should see an increase in our strength right here because we have a shorter member, and shorter members tend to be stronger. And it's not just a linear increase. A little later on, we'll take a look at the formulas for this, and you'll see that it's quite a bit more than a linear increase. So let's come along right there. That's nice and square. Well, we know that this one failed. The previous one failed at 22. So I'm going to start this at 25 just to be sure. Put the same amount of weight out here at the 50. And notice that it's not even buckling or pretending to buckle at 25. I'm going to bring that in all the way to 20. I'll turn it this way because I know which way it's going to buckle. If it buckles, it always buckles in the narrowest direction. And you can see it's stronger already because now we're down to 20 millimeters. As I keep moving it that way, it keeps getting, it keeps showing me a stronger and stronger force. So here we are at 15, 16, 17 millimeters out. It's holding up at 15 millimeters out. Holding up just fine. At 12 it starts to buckle. At 13, once you get that first pop, it's a good thing we know it held at 15. Does it hold at 14? Doesn't hold at 14. So now we know that that one holds at 15. So we can do the same formula right here. But instead of dividing by 230 on the bottom, we're going to divide by 150 millimeters on the bottom. And yes, that's rather awkward to write that in there, but let me just punch that in. So we've got the torque that comes from our arm. The moment of the arm is 0.41 newtons times 268 millimeters equals 109.88 Newton millimeters, because it's always really important that you keep the units together while you're doing that. 2 newtons times 500 millimeters, really easy to do. That's 1,000 Newton millimeters. Actually, that works out to be exactly 1 Newton meter. For those of you who are used to torquing up parts on your bike, you'll torque things up to like 4 Newton meters of torque when you're using a wrench on your bike. So 109.88 plus 1,000 Newton millimeters gives me a grand total of 1109. 0.88 Newton millimeters, which is the exact same torque that we had the time before, the exact same combined moment, because the weight was at the same place, the arm weighed the same, and its centroid was in the same place. The difference being that instead of dividing by 230, now I divide by 150 because I'm in closer. So if I divide that total by 150 millimeters, the millimeters cancel out, and I get 7.4 Newton. So I jot that down on my chart right here. That was, what did I say, 250 long. So in case of any doubts, you can measure. Where did that sample go? Yeah, measuring stick works good, but you can come right in there. 250 millimeters. Looks like I don't have space for 250 on the chart. We can add another column in there at 250, 7.4 newtons. And importantly on the graph now, where did my graph go? Record that on the graph. 7.4 at 250, that was 5. Okay, 6, 7.4 on my graph right there. Okay, I'm going to take a few more measurements and then I'll talk about how we analyze some of this. I should just record this and play it back at high speed, but okay, here's the 200 millimeter long sample of 3 millimeter by 4 millimeter nominal. I've increased my mass out here. I've left it at 500 because that's just such an easy place to do the math at. But you know, we could play around with the location of that mass. If you need something lighter, if it's breaking too easily, you can put it on the inside. For some of the really narrow ones, if you want to get rid of the impact of just the moment of the arm, there is a centroid right here, and you can use that as the pin right in here, and then the mass of the arm balances out. But we're not going to do that right now. And here I am. I'm holding at 40 centimeters, 400 millimeters. You can see I have to use my fingers right out here just to keep that stable from side to side. I'm not actually squeezing on it or providing any vertical force right there. Let's bring that in to 35. And it's holding steady. $300, it's holding steady. 250 or 25 centimeters. Starting to buckle in there. And you can see that curve starting to form. Now what's really interesting, at this point, if I take the load off, the curve goes away. So although this member is actually, from a structural point of view, really starting to get into failure there because it's changing shape, it's an elastic deformation. And that means that the elastic modulus for the material is far more important than its ultimate tensile strength or its yield strength when it comes to long, slender, buckling failure. We're still dealing with long, skinny, or slender members. When you get into shorter members, they buckle in different fashion, so elastic modulus is still important, but it's not the be-all and end-all. Out here, the elastic modulus for our slender members is really important. And here we go, we're at 21 centimeters, and it's holding, but I take it off, and it pretty much pops back to normal. Let's try 20 centimeters right here. Again, keeping sure that everything is nice and square. How long? I guess it didn't hold for that long. So we can say that it held at 210 millimeters, and we can do a bit of math on that. Now when I calculate that out, that came to 12.4 newtons, and I just wanted to remind you that when you're placing that onto the log chart here, that remember this is 10, and this is 20 right here. So 12.4 is pretty close to 10. You don't come up 2 notches right on here because that would be 20 and 30 right up there. You've got to place it, and you kind of got to eyeball it in here and say, well, 12.4. I don't think you're going to get 0.4 into that graph, but you can definitely get the 12 right in there. Okay, I'm going to test a few more samples. Okay, I've got a 150 millimeter long sample right here. Now, for reasons that I'll get into later when we take a look at the buckling formula for a slender member, or Euler's buckling formula, I know what a 300 millimeter member buckled at, and this is half the length. Okay, so the length, the strength, okay, should be inverse to the square of the length. So in other words, if this 150 is half as long as the 300 millimeter one, okay, a half, that's a factor of 2. 2 squared is 4. This was 4.8. I'm expecting something about 4 times as strong right in here. So I'm expecting somewhere around 20 newtons. And I'm being bold by saying this right now because I haven't done the test. Let's see where this fails and see if it comes out to 20 newtons, because if it does, then the universe is in a happy place right now. And if it doesn't, then apparently everything structural engineers have known for centuries is off. So here we go. I'm down to 20 centimeters. We're starting to see buckling. 15. There we are. Third. Okay, will it hold at 13? That was 12. It's holding at 13 out. I don't know if it's going to hold at 12 out. It didn't. So 13 centimeters, 130 millimeters is how far out we are. I love it when physics works. Okay, and actually physics would tell me physics always works. I just calculate it wrong sometimes or don't fully understand it. But I love it when I fully understand what's going on and my calculations work. And look at that. The 300 millimeter one, 4.83, so let's say 5, really close to 5. And I said that because of Euler's buckling formula for long, slender members, doesn't work for the really short, fat ones, but for long, slender members, because we've cut the length in half, it should be 4 times as strong, okay? Because it's a factor of 2 when you cut the length in half, and something should therefore be 2 squared, 4 times as strong. We go from basically 5 out here, cut the length in half, and we're at 20 right here, 4 times as strong. Physics is winning today. Okay, here's my 120 millimeter long member, and I've up to a 10 Newton weight out here, a 1 kilogram mass. So in Earth's gravity, we ballpark that. It should be 9.8 newtons. So as long as you know it's G equals 9.8 meters per second we're doing okay. We just rounded off to 10 for our calculations. And this will require a little bit of additional support. I could have made this member thicker. Making it twice as thick would have actually made it, I think, 8 times stronger. We'll talk about that and why that happens as well. But you may need, now don't support this, but you may need to use a couple of fingers, again, just to keep it from twisting. So here we go, we're holding at 30. And as we get shorter and thicker members, the stresses really start to go up, and that arm really starts to want to twist. And the failure is starting to move into our arm right now, but that's okay. Just use your fingers to brace that in there. If we have to, we can put a little bit of glue in the structure. This, I thought the one I was grabbing had all been glued together, but not quite. And there we go, we're coming in right here, and ooh, this one's quite strong. Coming in right here. So it broke at the 10. It was somewhere between the 10 and the 15. Now, as you get to the heavier loads, our apparatus is going to become a little bit more stressed, so the numbers you get might not be quite as good. Now, one thing you'll notice about how this one broke is that rather than getting that nice springy boing, boing, boing elastic failure that we had in some of the long members, this failed. Rather than classic Euler buckling, This failed in a method known as annealing. So the stresses in here built up so high that by the time this popped out to the side and went crack like that, the stresses in the inner and outer membrane, in this case the outer membrane right here, because you can see that the failure occurred in tension right out here, bent out this way. The stress in that member had already exceeded the yield stress, and in this case the ultimate tensile stress of the material right in the outside right here. So we've actually switched into a method of failure known as intermediate buckling right here, and so we're no longer constrained by Euler's formula. We've got different failure modes happening here because of the material properties at play and the way that buckling failure happens. So in any case, I'm going to say that one failed at about 12 centimeters out right here, because it was somewhere between 10 and 15. And I think that's about as accurate and precise as I'm going to be able to get off this chart. You could try a couple of the shorter members on here, but that's getting pretty strong. To get anything off the shorter members, you may need to go down to the 3 millimeter or the 2 millimeter nominal widths, where the additional thinness that you see in there is actually going to play quite a role in their strength. Okay, so do a bit of math here. Let's see what we got. Now, once you start to get data points for a particular cross section, you can start to join them together with a nice smooth line. And the nice smooth line should help you to predict the strength at intermediate points. So for instance, if your truss design later on requires you to have a 170 millimeter long member, and you need to know, will a 4 millimeter wide member support the load that I've got, you can come right in here and you can get a pretty good estimate for the strength of a 170 millimeter long member by coming right up here, reading that off and saying, oh well, I'm between the 10 and the 20 marks on my graph. I'm closer to the 20 side. I'm probably looking at a compressive strength of 16 or 17 newtons right in there. I'm also going to show you some mathematical ways that we can use our data to calculate what we've got coming off that chart, maybe a little more precisely than just eyeballing it, but you know what? Eyeballing it works pretty good too. This is starting to be a nice looking graph. Now, obviously, one set of data for just the 4 millimeter is not going to be enough to do all your calculations for your trusses. And this is why it's good to do a few different thicknesses, and it's good to have people in your class that you can share data with. Because if you do a series of 4 millimeter ones and your friend does a series of 4 millimeter ones, the first thing you'll be able to do is compare your data and make sure that you're doing the math right and that you did your testing right, because you should get very similar numbers. As you can see, our apparatus within the range in which it works is actually reasonably accurate, okay? And you should be able to compare your numbers right here. And because this is not a lab that you have to write up for an original assignment, share your data, okay? Compare your notes. Copy what other people have done and let them copy what you've done, because you're trying to build up a database of compressive member strengths that are going to help you later on when it comes to designing your truss. So put that together, and then you'll have ones for the nominal 4 millimeter. Somebody else will do one for the nominal 3 millimeter and the 2 millimeter, and then you'll start to have this chart, and the 2 millimeter one should be weaker all the way along than the 4 millimeter, and somebody might do a 5 millimeter one, which should be stronger all the way along as well. Now you will reach a point where our poor little apparatus right here is no longer sturdy enough to do the testing, and at that point you can just say exceeds the apparatus strength, and you can see right in here I've left that off right here. As soon as you start getting into the kneeling, the forces start to go up quite a bit, and this apparatus might not be ideal for doing your calculation. If you press hard enough on a sample and you get a really short sample right here, this one will still fail by annealing, I think, but if you got down to like a 1 centimeter long sample right here and you braced it in a compressive tester really nicely, you would actually get a true compressive failure. It wouldn't fail by buckling, but you'd actually start to press on it so hard it would be so short that it wouldn't be able to pop out to the side. And what you'd see happening is as you press down, of course, you know from tensile testing that when you pull something and make it longer, it gets skinnier because the amount of material in there can't change. When you press down on here, this is going to get shorter, which means it's going to get thicker. And as it starts to get thicker, it's going to start to expand out to the side, and that's going to create tensile stresses in the middle right here. And what you'll actually have is an internal tensile failure. And certainly I'll have to see if I can find some videos of compressive testing of concrete, because when that goes, you'll actually get a cone left at the top and a cone at the bottom, and all the rest of the material will pop out to the side. Creates a glorious mess and a lovely big bang sound. Used to do that with my high school students at David Thompson. We'd take toilet paper tubes, pack them full of cement, see who could make the strongest mixture, pop them in the compression testing machine, and then we'd blast cement all over the shop. And I quit doing it because it was just such a mess, both to pour the cement and to clean up after you did your compressive testing. But it's too bad because the kids really liked it because, well, I mean, look at our little testing apparatus and the jump that you got out of me when it failed. Anyway, time to take that and put it into context of some overall mathematical formula now.